All right, welcome. Happy Friday. Hope you're doing well. We're going to continue our investigation of series and series tests today. But start off with a little bit of practice and answering some questions that have come up, okay? For the start here, I'd like you to try these first 4 warm-up questions that you see here at the top of the page. I want you to, for each of these series, find either a piece series or a geometric series that would be appropriate for comparison, and then use the direct comparison test or the limit comparison test. Some of these work better for one, or you can use only one. Some of them kind of either is fine to determine whether each series converges or diverges, all right? So I want you to give that a shot. Here are the 4. Go ahead and use the an appropriate P-series or geometric series to do a comparison, either limit or direct. Pause the video and come back when you're ready. All right, let's take a look. All right, so this first series here, I'm seeing 3 to the n over 5 to the n plus n. This looks like it's trying to be something like geometric because we have some number to the n over 5 to the n. In fact, if we kind of ignore this plus n because these exponential things will be bigger, this looks like it's a good comparison to, so let's compare to 3 to the n over 5 to the n. Maybe a direct comparison will work here. Let's try. So if I have 3 to the n over 5 to the n plus n, how is it going to compare value-wise to 3 to the n over 5 to the n? Okay. Well, they're the same except for in this one we're adding into the denominator. So we're making the denominator bigger. Making the denominator bigger will make 3 to the n divided by this thing smaller than this one because we're adding something to the denominator. So this guy will always be less than our comparison, the thing we're comparing it to. Well, what do we know about 3n over 5 to the n? Well, we know that that series is geometric. And it's a geometric series. It's a geometric series. My r value, what would I be multiplying by each time? It'd be 3 over 5 because this is really the same as n equals 1 3/5 to the n. So my r value is 3/5, so it's a geometric series with the absolute value of r being less than 1. So the series that I'm comparing it to, 3 to the n over 5 to the n, converges. What does that mean for us? Therefore, so my comparison series converges. The terms of my series are going to be less than those, so the sum of mine is definitely going to converge. So therefore, by the direct comparison test, my series converges also. Alright, so I use the direct comparison test there because I think it's a little easier because it's a pretty quick comparison to realize these terms are less than this, and the series of this is going to converge, therefore mine converges. Remember, for divergence, I would need to figure out that my terms are going to be bigger than something that diverges. For convergence, I need to know that my terms are going to be smaller than something that converges. Okay? So let's see the next one. N squared over 1 plus n. This looks relatively simple. I see n squared is going to win on top, n is going to win in the denominator, so maybe, if I did a limit as n goes to infinity. So maybe the limit comparison test will work here, and I'll compare to n squared over n, which is just n actually. Interesting. Alright. So what do I know about just n? Well, this series, n equals 1 to infinity of n, diverges. How do I know? I guess we could say the nth term test, because the limit as n approaches infinity of n does not exist, because it's infinity. So I do know that this comparison series n that I'm comparing it to diverges. Alright, so let's do my limit comparison now then. My limit comparison test says, okay, if I take the limit as n approaches infinity of my original thing, divided by the thing I'm comparing it to, let me find that limit, and I can make my conclusion. Dividing by n, that's the same thing as saying the limit as n approaches infinity of n squared over, dividing by n, same thing as multiplying by 1 over n. So I'm going to multiply n into both of those, n plus n squared. Alright, interesting. So what happens here? Well, as n goes to infinity, I could use L'Hopital's rule or just my limit processing here. As n goes to infinity, I would get n squared would be dominating on top and n squared would be dominating down there. Limit as n approaches infinity feels like n squared over n squared, which will be 1. Okay, so my limit comparison test gave me a number. Remember my limit comparison test, a number between 0 and infinity. This is that. If you get a number like that, then both of our series either diverge or converge. In this case, I already knew that n diverges, so I can say therefore by the limit comparison test, my series diverges also. Why? Because the thing I'm comparing it to I knew diverged. I did my limit comparison steps and got a number between 0 and infinity. So by limit comparison test, my series I'm comparing it to diverges also. They do the same thing if you get a number between 0 and infinity, not including 0, not including infinity. Alright. So let's look at the next one. Looks kind of similar. These ones where we have like power things, not exponential things, but power things like 2s and 3s or squares and whatnot, oftentimes the limit comparison test is good. So let's do that. Let's compare to, let's see, 5n squared over 2n cubed. If I kind of simplify that, that seems like it's going to behave a whole lot like n squared. Cancel out some n cubes. It looks like it'll behave a whole lot like 1 over n. 1 over n. And what do I know about 1 over n? Why did I get, well, first, why did I get 1 over n? Because n squared divided by n cubed will give me 1 over n, so that's what I'm going to go with here. I'm going to ignore the coefficients because they're just factors. They'll multiply in each term. So let's see. What do I know about 1 over n? Well, that series is the harmonic series. I know the harmonic series diverges because it is a p series with p being less than or equal to 1. And that's our problem. P series diverge if p is less than or equal to 1. In this case, p, my power there is 1. So this is going to diverge. Let me do my limit comparison test, and I know my comparator diverges. All right. So I need the limit as n approaches infinity of my initial thing, n squared over 2n cubed minus 1, over the thing I want to compare to, which is 1 over n, divided by 1 over n, same thing as multiplying by the reciprocal. So multiply the reciprocal up there, so that'll give me 5n cubed over 2n cubed minus 1. I could use L'Hopital's rule here to figure this out, or I could just compare, okay, 5n cubed is going to dominate on top as n goes to infinity, 2n cubed is going to dominate underneath. The limit as n approaches infinity, excuse me, 5n cubed is going to dominate on top, 2n cubed will dominate down there. And what does that leave us? It leaves us with 5 halves. 5 halves is a number between 0 and infinity, non-inclusive. Therefore, by the limit comparison test, my series 5n squared over 2n cubed minus 1 diverges also. My comparison series diverged. I did my limit comparison test, got a number between 1 and infinity. Therefore, my initial series, wow, you didn't see it, my initial series diverges also, because my original series that I was, because my comparison series diverged and my limit comparison test gave me a number between 0 and infinity, my series I'm interested in will also diverge. Okay, last one, 1 over 25n plus 16 summed up. All right, using a similar process, let's see, I got just n things, so let me compare also to 1 over n and see what happens here. As I stated above, I know that that series is the harmonic series, and I know that it diverges because it is a p series with p is less than or equal to 1. So let me use that in my limit comparison. My limit comparison will be the limit as n approaches infinity of 1 over 25n plus 16 over 1 over n. Got a little crammed there. Multiply by the reciprocal, so that gives me the limit as n approaches infinity of n over 25n plus 16. Alright, n will dominate on top, 25n will dominate underneath, or use L'Hopital's rule, that will give me n over 25n, which will give me 1/25. Again, a number between 0 and infinity, non-inclusive, therefore by the limit comparison test, my series that I'm looking at also diverges, because the series I was comparing it to diverges also. Alright, so there's the warm-up. Hopefully that helps get you a little more practice in thinking about these comparison tests, and we'll get some more chance to practice them as we go. But there are two questions that have arisen that I want us to talk about, and so I want to answer them now that have come up in different people I've talked to, our conversations, okay? One is, does it matter what the index of the sum starts at? Sometimes problems begin with p equals, that should say n equals 0. Sometimes the problem begins with n equals 0, sometimes n equals 1, sometimes n equals 2. I'll change that on the PDF. This is a very good question, and I appreciate how perceptive you are in looking at that. For our purposes right now, generally speaking, no. Reindexing and changing indices and things like that is a more complicated conversation. But for now, short answer is no, and here's kind of why. If we know, for example, that like, we'll do two ones we know. So let's say, for example, we think about like 1 to infinity of 1 over n, which we know diverges. It diverges because essentially the sum is infinite, right? Well, if I started that sum at n equals 2 and tried the same thing, essentially I'm saying, hey, let me take an infinite thing and chop off the first term. Well, chopping off the first term doesn't change the fact that this thing will be infinite and diverge. Generally speaking, then changing that beginning index doesn't particularly matter for the things we're looking at right now. If things come up, I will flag them for you. But as we are just getting into this whole idea of summation and things like that, just leave it like that. For now, it doesn't matter, especially because we're just dealing with like n's or counting things being positive or 0. That doesn't impact anything of ours. It certainly doesn't impact convergence, because if you take like something that's converging, like this p series with a p value greater than 1, it converges. And if you were to like change that index and do the series from n equals 1, let's say like n equals 2, 1 over n squared, well, we're just chopping off the first term. So this will just make, if this converges because it got small enough, then this certainly will, because we're actually just chopping off the first term. All right. It's not a hard and fast rule, but for now, those are the things that we're going to be looking at. All right. The other thing that people are asking is, how do I know which test to use? That's a great question, and you're already thinking a few days ahead of me. We'll get a little more practice with determining what tests and things to use. For now, I would say that there's some foundational things, like you should recognize and know P series, and the fact that they converge when P is greater than 1. You should recognize geometric series, and the fact that they converge when the absolute value of R is less than 1. Those are kind of our foundational things. And then think of the other ones as different tools. I like to go to the nth term test if it's a quick one. The nth term test will very quickly let you know whether or not something diverges. And then from there you can branch out into our different tests. And you'll start getting a sense of which tests work for different kinds of functions and how they look. Some of them are, in my opinion, easier to apply than others and are kind of nice. I particularly really like the limit comparison test, if I can use it. But at this point, we've also learned the direct comparison test, the integral test, today we are going to look at, let me make sure I haven't missed one that we've done. Today we're going to look at the alternating series test. We'll also look at the ratio test. So we have a whole series of tests, and just think of those as tools in our toolbox, and you'll start picking up on some of the patterns. However, the short answer is how to know which test to use. Until you got a lot of experience, you build off this foundation. This is a quick test for divergence. Then you cut to these. Without a lot of practice, it does feel a little clunky. And there's a lot of things to remember, because you got to remember how to apply each test. That is something that we're going to have to work on, and just take the time now to start going back, reviewing each test to know when and how it applies will be really, really useful. I include those things on the blue sheet, the cheat sheet that I gave y'all to before the benchmark test. So for now, this is sort of the structure of our thinking. Short answer is, it takes practice and work on trying to pick up on the patterns about which tests are useful for different kinds of series along the way. But I'll try to flag them as I've done in videos too, which series are useful, which tests are useful for which kinds of series. All right? Well, let's look at another test. We have seen already some alternating series. We've seen them a couple times. For example, yesterday we saw the alternating harmonic series. All right. The alternating harmonic series looked like this: 1 to infinity of -1 to the n plus 1 over n. Although for these alternating series, it doesn't really matter whether it's n plus 1 or so, as long as that term is alternating the sign of the term is alternating every single time. And we said that this alternating harmonic series, converges, even though the harmonic series diverges. And I said, hold off on this. We'll see that soon. Well, the harmonic series we know diverges. Today we're going to talk about this alternating series, talk about convergence. There is, for these alternating series, a quick test for alternating series to determine if they converge. But that's the thing here. This test only tests convergence. So in that sort of, unfortunately, nebulous kind of holding things in your mind for series, the alternating series test only tells us if an alternating series converges. Okay? And here's what the alternating series test says, though, because it's relatively simple. The series 1 to infinity of -1 to the n plus 1 times un some term. So alternating, because -1, as we add to the exponent, we'll keep alternating sign, which gives us u1 minus u2 plus u3 minus u4 plus, as long as it's alternating back and forth like that and follows some rules, then it converges if the following conditions are satisfied. There are 3 of them, 3 conditions. Each un is positive. What that really means here is that sign changes every term. No exceptions. Okay? The only thing that can change sign is the -1 to the n plus 1. If the rest of the thing ever changes sign on you, we got problems. It needs to alternate back and forth. We can't have u1 minus u2 minus u3 plus u4 minus u5 double minuses there. No, it's got to alternate every single time. All right. 2. un has to be greater than or equal to un plus 1 for all n is greater than or equal to big N for some integer n. That sounds really complicated. Basically, what are we saying? We're saying that some term has to be greater than the next term for all little n's bigger than some n that we can pick. What does that mean? It means that eventually, if un is bigger than the next term, that means the series is decreasing. Eventually, the sequence decreases. It doesn't have to decrease right away, but eventually the series needs to decrease. Okay? The series of the u parts of it, it's basically ignoring the sign. Some people say the absolute value of the terms. So the un part of this, eventually the sequence has to decrease, or I should say the absolute value of the sequence has to decrease. Okay? So without the signs, those numbers have to be getting smaller eventually. And finally, the limit as n approaches infinity of u sub n, again ignoring the signs, that the limit has to be going to 0. Alright, I again made another mistake in here that I will delete on the PDF. And you'll notice here that I'm about to cross out that the rest of this line is completely unnecessary. So I'm going to get rid of it. I'm not sure why it's there. 3 is kind of self-explanatory, that the limit as n approaches infinity of the un part, ignoring the signs, that the actual absolute value of the terms has to be going to 0. So it's kind of like the nth term test, but we want it to go to 0 this time. So every sign has to change. The sign changes every term. Eventually, the absolute value of the sequence decreases, and the limit of the terms without the signs has to be going to 0. All right. Essentially, what happens with alternating series, then, if you kind of visualize it, with alternating series that converge, is the partial sum as we add up more and more terms. The partial sum to some n value keeps like overshooting the limit and back and forth because we're adding, then we're subtracting, then we're adding, and we're subtracting, but we keep doing that in smaller and smaller intervals until it closes in around some limit as the n value approaches infinity. Again, another typo, but infinity there. I'll change all these things on the PDF. All right. So let's determine whether the given series here converges. All right. We got 3 things to check. First, will it alternate every term? Sorry. Will it alternate every term, and that un is always positive. So if I take out my alternating term, because that's going to make it alternate every term. If I take it out, is 1 over, I'll move it out front, is 1 over square root of n always going to be positive? My un part, yes. Square root of n is positive. 2. Is un, u sub n, going to be greater than or equal to the term that follows it eventually? Well, if I plug in like 1, and I plug in 2 for n, then 3 for n, then 4 for n, yes, this thing will be decreasing. In fact, this one decreases always. Yes, I can say 1 over the square root of n is greater than or equal to 1 over the square root of n plus 1. Finally, 3. What happens to the limit of my u sub n thing? Well, the limit as n approaches infinity of 1 over the square root of n, as n grows, will go to 0. So this meets all of my requirements. It's an alternating series. The rest of the terms stay positive. The term before it will be greater than the term after it, all the way through. And the limit of the terms goes to 0. So I can say by the alternating series test, this sum, this series converges. Remember, this only tests convergence, not divergence. If we get something that doesn't work, we can't use this one, but it tests convergence. Again, it tests convergence, so there are situations where it just doesn't apply. Not that the series diverges, but that the alternating series test does not apply. So in this, for each series below, explain why the alternating series test does not apply. Okay, does not apply. All right, let me separate this out. N equals 1, negative 1 to the n plus 1, cosine of n over n squared. Let's test each of our things. All right, first I want to know whether or not this u sub n, the rest of this stuff, I know this part are alternate, does the rest of this stuff always stay positive? Cosine of n. Cosine of n. Well, cosine of n, as n ticks up, is sometimes going to be positive and sometimes negative. So I gotta say that the cosine of n over n squared, yeah, n squared stays positive, but cosine of n, depending on what I plug in there, will not be. I gotta say is not always positive. Therefore, the alternating series test does not apply. We could have kept going and checked the other things. We have to make sure that eventually the term before, where is it? That eventually the term before is greater than or equal to the term after, that this is decreasing eventually. We could have shown that for cosine of n over n squared, so that part would be okay. And the limit of that as n approaches infinity will go to 0. The problem is this cosine means that my term that's not alternating is not always going to be positive, so we're going to run into alternating troubles in there. Okay. All right. Let's see. I've already separated this one out. Let's see what its issue is here. 1. As n goes to infinity from 1 is 3n plus 1 over 10n minus 5, going to always be positive. 1 and 1, that'll be positive over positive. Yeah, as n grows, this is always positive. Okay. So that works. 2. I need to know whether or not this thing will eventually decrease. Okay. Well, I know it will, because we could show that 3n plus 1 over 10n minus 5 is going to be greater than or equal to 3n plus 1 over 10n plus 1 minus 5. Because this is going to multiply by 10, this is only going to multiply by 3. This bottom part is going to grow faster. So this thing is going to eventually get to the point where it's always smaller than the previous term, because that times 10 in the bottom, right? Okay. Check my third thing. So far everything's been okay. This thing will eventually decrease, because that 10 times n is going to win in the bottom. Grow faster than the top. But let's check, because in the end I also need to make sure that the limit of my terms that are not alternating, not the negative 1, is 0. So let's do that. The limit as n approaches infinity of 3n plus 1 over 10n minus 5. Now, there we go. I could do my L'Hopital's rule or something like that if I want to, but I could also just realize, wait a minute, 3n's going to win up top. 10n's going to win below. And that limit is 3/10. There's my problem, that the limit of my terms actually doesn't go to 0. All right? So I gotta say, therefore, so I should say actually the limit as n approaches infinity of 3n plus 1 over 10n minus 5 does not equal 0. Therefore, the alternating series test does not apply. Need not apply. All right. So here the failure was that the limit as n approaches infinity of the series without the alternating part does not actually go to 0. All right. Be on the lookout for this. In fact, on the AP exam, they like to ask about why what series doesn't the alternating series test apply to, or why doesn't it apply, and things like that, rather than actually applying it. All right. All right. What I'd like you to do is take a few minutes, and I want you to try the series of series questions below. There's 4, where I want you to determine whether the given series converges using the alternating series test. You don't have to go past that. I just want to know, using the alternating series test, does the series converge? And then the bottom, explain why that series, the alternating series test, cannot be applied to the series below. All right. Pause the video, give it a shot, and come back when you're ready. Okay. Here we go. We want to determine whether the given series converges using the alternating series tests. As we saw, we have 3 things we need to check. First thing to check, number 1, we need to make sure that our term here that is not part of our alternating part is always positive. And from 1 to infinity, n is always positive. So that's fine. 2, we need to make sure that eventually n decreases. So I'm going to compare, is n greater than or equal to n plus 1? Actually, the answer is no. It's not greater than or equal to n plus 1. So the alternating series test does not apply. If you wanted to go to a step further, we could actually probably tell that since n is just going to grow, it's going to keep growing, this whole series is actually going to diverge. You're going to get like 1 minus 2 plus 3 minus 4 plus 5 minus 6, and it's never going to converge to anything there. Okay. Not part of what I asked, but an extra little tidbit. Okay, next one. We need to check to make sure our terms here, minus the alternating part, is always positive. 1 over n squared is always positive as n goes from 1 to infinity. 2, we need to check to make sure 1 over n squared is going to be bigger eventually than 1 over n plus 1 squared. And let's see, 1 divided by some number, 1 divided by a bigger number. This is going to be smaller than that one, so yes, this works. 3, we need to make sure that the limit as n approaches infinity of 1 over n squared is 0, and as n approaches infinity, 1 divided by a bigger number will give us 0. So we can say, therefore, our series converges by the alternating series test. This one passed everything. Hooray! The u sub n terms here were positive. As n grows, eventually the sequence will decrease because we have 1 over n squared. It will be greater than the term that follows it. This thing will be decreasing, and its limit goes to 0. Next one. Okay. 1, need to check to make sure this is positive. N over 2 to the n. Let's see, since n is going from 1 to infinity, that's positive. That'll stay positive. Yep, this is always positive. That's actually a good attitude to have nowadays what's going on, always be positive. We'll be okay. 2. What do we need to check? Oh, we need to check to make sure that the series eventually decreases. Interesting. So, n over 2n, I want to compare it to what happens eventually with n plus 1 over 2n plus 1. Now we can think about the strength or even like the derivatives of these and how they grow. N is going to grow linearly. 2 to the n is going to grow exponentially. So the denominator is going to get bigger faster, right? So eventually it'll win. It'll take over. And so yes, this thing will eventually be smaller than the previous term because this thing's going to grow so fast, right? You can, if you start plugging numbers, you might be able to even see that, right? We'd have 1/2 as our first term, and the next term would be when I plug in 2, how do you get 3 over 4? You might go, that didn't work. It's growing. You're right. But then my next term, when I plug in, will give me, oh, I say 3 over 4. That should be 2 over 4. And it's staying the same. Sorry, I plugged in 1, 2 to the 1, 1 over 2. 2 to the 2. Then I could say 3 over 2 to the third is 8. 4 over 2 to the fourth is 16. Yeah, it's going to start decreasing eventually. 3. Thing I got to check is the limit now. The limit as n approaches infinity of n over 2 to the n. All right. Could use L'Hopital's rule here if we want to. This actually may be a good application if you're having trouble looking at this. But we do know as n goes to infinity, n is going to grow more slowly than 2 to the n. That's what L'Hopital's rule proves. That by L'Hopital's rule, we can apply because it goes to infinity over infinity. That this is going to be equivalent to the limit as n approaches infinity of derivative of n is 1 over the derivative of 2 to the n. This is a good reminder, right? Derivative of some exponential thing that's not e to the x is the natural log of the base 2 to the n, and so yes, the denominator is going to win because then it'll keep growing. This goes off to 0. So does it meet everything? It's always positive. It eventually decreases. The limit of the terms is 0. So yes, therefore our series n equals 1 to infinity of negative 1 to the n plus 1 n over 2 to the n converges by the alternating series test. All right. So our middle two converge. Let's check the last one. It's kind of interesting. Our last one, our alternating part's right here. So I'm really just going to focus in on the rest of it. 1 over 2n plus 3 to the n. Sorry, 2 to the n plus 3 to the n. All right. So number 1 over 2 to the n plus 3 to the n. Is it always positive? Well, as n goes from 1 to infinity, yes, those will stay positive. So we can say yes, it's always positive. 2, what's going to happen here? We want to check to make sure it gets smaller, so we got to compare 1 over 2 to the n plus 3 to the n. How does it compare to 1 over 2 to the n plus 1 plus 3 to the n plus 1? Well, we have 1 divided by something, and then 1 divided by, if we're adding to these exponents, it's going to be 1 divided by a bigger number. So this is going to be smaller than, because this number denominator is going to be bigger, it's going to be smaller than this previous term, so that's good. And test number 3, we need to make sure that it eventually decreases, that the limit as n approaches infinity of 1 over 2 to the n plus 3 to the n goes to 0. Well, as n goes to infinity, the denominator is going to get really, really, really big, so this does go to 0. Therefore, the series then, this should be my series symbol, sorry about that. My series n equals 1 to infinity of 1 over negative 1 to the n plus 1 times 2 to the n plus 3 to the n. What do I know about it? It met all 3 of my requirements. Positive, eventually decreasing, limit goes to 0. Therefore, it converges by the alternating series test. All right. Last thing, explain why the alternating series test cannot be applied to the series below. Okay, so we need to check everything, right? We need to make sure each term without the sign is going to be positive. It looks like it's alternating, but sometimes these things are set up to fool us here. So it looks alternating, but let's ignore the sign. So that first one, 1 over the cube root of 2 minus 4. Huh. Cube root of 2. Cube root of 2 is pretty small. Minus 4. Well, the cube root of 2 is definitely less than 4. So something less than 4 minus 4. This is going to make our first term negative. So actually it fails at the very start here. U sub n is not always positive. The alternating series test does not apply. All right. This next term would be positive with a minus sign. This next term would be back to being negative. Then this term would go back to being positive. Wait a minute. We got to think. So if this is actually negative, this one would be positive, this one would be negative, this one would be positive. But with the absolute value of that, of the absolute value of each of these terms, does eventually decrease? Because my intuition is here that it does not apply. But I'm noticing that this one would be actually negative, this one would be positive. Oh, no, never mind. We'd have a negative minus that. So it does not apply. I'm sorry. Ooh, I even wrote this problem and I threw myself off. The terms are not always positive, so the alternating test does not apply. That is actually, I would say, in terms of the AP exam, something they often will throw is like, are all the terms not actually positive if you go in and look at them? So be on the lookout for that. And then also checking to make sure that the limit goes to 0 is good. All right. Please make sure you do the check-in quiz. There's some textbook homework problems and then some assigned concepts. And do be sure you check the intervention list for who I need to meet with online next week and when that's going to happen. Have a great weekend, everybody. Please read all my announcements, and I'll see you later. Bye.